Welcome, fellow chemists, to the 9th and final, yes, final video on the reactions of the alkenes. Your reward for making it this far is the simplest reaction yet, so let's discuss the addition of hydrogen, also known as hydrogenation. Unsurprisingly, this involves an alkene reacting with molecular hydrogen. When butene is in the presence of hydrogen, no, nothing is wrong with your screen. Nothing happens when an alkene is in the presence of hydrogen. If you've watched some prior videos, you know where I'm going with this. Because the bond between the two hydrogen atoms is strong, extremely high temperatures would be required, and without them, the molecule will not react when it encounters the alkene. However, if we introduce a catalyst to this process, we can get it to proceed more easily. Platinum, palladium, and even nickel can be used to get this reaction going. When it does, it is literally the addition of the hydrogen molecule onto the alkene. See? I told you it was simple. But only if that were 100% accurate. The best understanding of how the reaction actually takes place is as follows. When a hydrogen molecule encounters the surface of the catalyst, it adsorbs or sticks to it as individual atoms. What happens to the alkene is different, but for simplicity, think of the pi bond breaking in a manner that results in each sp2 carbon bonding to the metal. When hydrogen and the alkene move across the surface of the metal and come in contact, the hydrogen atoms bond with the formerly sp2 carbons. The result is pretty straightforward. The double bond has been replaced by hydrogen atoms, and ethene has become ethane. This is also an example of reduction, as we are increasing the number of carbon-hydrogen bonds the molecule has. Hydrogenation is an exothermic process, and the energy released is called the heat of hydrogenation. Exothermic processes have negative delta H values, and a value of negative 30 is a reasonable one. It would also be reasonable to expect the heat of hydrogenation to be exactly the same, so naturally, when describing heats of hydrogenation, chemists typically refer to them as a positive value. If we can overlook this ridiculousness, we can use this value to our advantage. The reason being that the more stable alkenes will have lower heats of hydrogenation. This is especially useful when determining which isomers are more stable. Take these three isomers of butene. As we go from left to right, the isomer increases in stability as the heat of hydrogenation decreases. The stability is linked to how substituted the alkene is. A more substituted alkene has fewer hydrogens on the sp2 carbons. But1ene has 3 hydrogens, and the other isomers each have 2. Since they each have fewer hydrogens, they are more substituted and more stable. Of course, those other 2 isomers are the cis and trans versions of but2ene. The last conclusion we can draw from this data is that the trans isomer is more stable than the cis. Armed with that information, here are 7 structures for alkenes with the letter R representing an alkyl group. Given what you know now, try and rank them from most to least stable. The higher the alkene moves up the graph, the less stable it is. As the alkene becomes more substituted, the stability increases, which we observe in the data as ever smaller heats of hydrogenation. Although what chemists have done with the value of delta H may be unnecessarily confusing, the labels are nice and straightforward. Ethene is non-substituted and has the highest heat of hydrogenation. A monosubstituted alkene is more stable. A disubstituted alkene is more stable than the mono, with the trans version the most stable of the subset. The trisubstituted is more stable than any of the dis. And finally, the tetrasubstituted alkene is the most stable of them all. In summary, hydrogenation adds hydrogen atoms to the carbons of the double bond. The most common method is to utilize platinum, palladium, or nickel catalysts. Stability of the original alkene can be determined or estimated by knowing how much energy was released, how many substituents are on the sp2 carbons, or what type of isomer it is. The lower the heat of hydrogenation, the more stable the alkene is. The fewer sp2 hydrogens the alkene has, the more stable it is. Finally, for the isomers, the trans version is more stable than the cis. Coming up, we say goodbye to the alkenes and hello to the alkynes. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. Since hydrogenation involves potentially cis or trans alkenes, you should brush up on how to name and identify such molecules. As usual, feel free to get in touch with me via email, social media, or if you would like, make a request in the comments.